the general, the 3D stress is, say, tau ij equal to sigma x, tau xy, tau xz, tau xx. So this one, again, the first symbol indicate is the which plane is lying on, and the second one is on the direction. So this is the stress element in the x-plane. So for example here, in terms of this one, this is the x direction, y direction, z direction. Okay. So in this way, this is the first row indicate is the stress element on this plane. Okay. So I just want you to do this one, and then the second one is y, tau yx, tau y, and zz, tau zx, tau zy. And now to make assumption is this all the components regarding the involving z component will be 0. So here we're looking through here. Those one has involving z. So this one, this one, this one, this one, this one. 1, 2, 3, 4, 5 z component. Those components must be equal to 0. Or in real applications, as long as you can identify the 5 components, that has a very insignificant value compared to the other 3, then you can right away to assume that problem can be described by this. So basically, if this is a sheet metal, basically you can plug into the 2-dimensional without consideration of the 3rd dimension. Okay, so that is a simplification, and that is the assumption. So again, are you able to apply these conditions? Then that is a criteria for you to apply for. So under these situations, then you can see what is Hooke's law to govern the plane stress problems. So again, we're back to our original Hooke's law statement. Okay, that's a whole thing here. So this one, we simply put those components equal to 0. Okay, so putting here, we reformulate, we simplify the whole equations, and again, carefully, and that one will become like this. So from here, you can see on this side, I eliminate unnecessary information, take away the 0 things. So the big whole things, basically you just manipulate the algebra, the linear algebra, then that is the equation here. Okay. So for this is the governing equation for the plane stress problems. Okay, and in certain textbook, and the people try to find this equation is to relate the strain to stress, and on the other side you can relate stress in terms of strain. If you like to spend time to formulate, but it's not necessary. Those formula is available anywhere. So simplification, this kind of multiplication, this manipulation will take a little bit of time for you to do some kind of symbolic calculation. But here I summarize the whole thing for you. And so probably we can take a look at the one example to see how can we exercise the problem here. And so like you can see, I didn't spend time on the derivation of the formulas. And so once you prepare for doing your homework or prepare for your testing, so I think I would suggest you maybe download or print out those handouts and then box the necessary formulas for your future use. Okay. And so right now we stick with these formulas, and then So for example, if we consider this is a sheet metal, and this one has the Young's modulus Q900 KSI, and Poisson ratio equal to 0.02 and 0.28. So that is sheet metal. So right away we pick up this concept. We're going to go to the plane stress, and then we're going to base upon these formulas. And under these situations, we are given the dimensions here. This is 1 inch. And then, under given these information, we're going to apply the loading and the constraint. The loading is this. On the top, we apply a uniform traction. We apply the uniform stress. Sigma y equal to positive 5,000 psi. So basically, the stress is to pull up the material. On the other side, this material is kind of fixed. It's not fixed. The bottom side is, this is a roller, okay? This is the symbol. This is the symbol for constraining movement in the y direction. So basically here, this model is like this. Is the bottom side won't move away from the ground, but this material, because due to stretching, is allowed to shrink freely in the x direction. So that means the deformation would look like this. So here is the final deformation this material look like. Okay. So again, using this roller, that is to confine the gravitation in one direction. So under these situations, we want to calculate the first one is the deformation in x direction, and then deformation in y direction. So we can pick up this formula here. And for this case, if without giving you the hint, this can be solved by plane stress problems, then your job is you have to analyze from the beginning to justify whether this equation will be good for you to continue. Okay, so that is your job. Okay, right now we start from here. So from here, from that formula, this one will be equal to minus sigma y. Okay, and then epsilon y equal to sigma y divided by e minus mu sigma x. So now we plug in the information here. And for the sigma y, this one is given 50,000. So this is 50,000. And anything else? We given the e, yeah, right? And new. Okay, so those one here. And anything more?
We can figure out strain of y because we have the phenomenon of it.
Okay, so right now we look at this one. This has two equations, and we have basically x, y. Basically, we have four elastic parameters. So we need to figure out two of the four. Otherwise, we wouldn't be able to solve for the other. So right now we know this one. This is okay. Okay, this one is. How about this one?
Should be 0.
That should be 0. Why this one? Okay, this one is 0. But the question is why this is 0. You can see this material under deformation is free to deform free to deform in the x direction. Free to deform, that means that is under no stress. And that is the, right away you have to pick out that concept quickly. Okay? So that is 0 here. So right now we can be able to solve for
Can you explain why stress of x is 0 again? Is it
Which
just
one?
because there's nothing being, no force being applied?
Yes. Okay? So there's a no force, a substitute no force. Okay? So for this case we can solve for, and